Hello, everybody. Welcome to Standards Power Hour. Today, we're going to be talking cam, crank, precision measurement. So we're going to get into it. We're going to start off with a few slides here. So as we're going through the Power Hour here, we first are going to discuss the cam and crank sensors. Cam and crank sensors could be two-wire position sensors. Now, if they're two-wire position sensors, they're going to create an analog signal. That analog signal, as we can see in this description here, is produced because the sensor itself has a magnet and a coil of wire on it. And then there's a reluctor, a metal reluctor that passes by our sensor. And as that reluctor passes by, it's going to generate a voltage. So as the reluctor, whether it's a cam or a crankshaft, moves past the sensor, we create that analog voltage. The faster the reluctor spins, the more voltage we create. So critical factors are the rotational speed, okay, especially if you're starting a cranking of the engine. We need to have a couple hundred RPM, 150, 200 RPM minimum for the sensor to get a good enough signal. The strength of the magnetic, the magnet, and of course the closeness of the sensor to the metal. The air gap is critical for the sensor to work properly. Now, let's take an example here. And this is a typical two-wire crank sensor. And what you have here is the sensor, two wires going back to the computer. One is going to be a positive wire. One is going to be a ground wire. And that signal is going to be created depending on the year, make, model, and the version, where one wire may be at ground, or we may have both wires creating a signal. And we'll show you one of those examples here in a minute. So as that reluctor moves, okay, we're going to be creating that voltage. And again, the speed of the reluctor depends on the voltage level we're going to get out of the sensor. Now, depending on the actual sensor, okay, and the manufacturer, the computer may have a bias voltage on the wire. Now, not all computers are going to produce this, but some will be at 0 volts. Some will have a 1.5 volt DC bias voltage on it, and that could be both on the positive and negative wires. Okay? It could be just on the positive. It depends, again, on the manufacturer. Or we could have about a 2.5 volt reference. Now, these are DC voltages on the circuit, and that is for part of the testing of the circuit. But the sensors produce that analog or AC voltage. Now, the key here is that the DC and the AC can coexist. The AC voltage will ride right on top of the DC voltage like it's not even there. So here's an example of that. Okay, we have a DC voltage showing approximately 2.6 volts. And if you notice, that is showing the ground. So let me just bring my mouse over here. And we can see that where the ground level is actually at 2.6 volts DC, both on the positive crank sensor wire and on the negative crank sensor wire. The AC voltage is riding right over top of it, like the DC is not even there. So the DC is for the circuit detection, for setting codes, and the AC is the actual signal being produced. So that is an average, that's a common two-wire sensor. We also have three-wire sensors involved in the systems, okay? And they could be king, they could be crank, they could be cam sensors. A three-wire sensor is going to have a power supply, it's going to have a ground, and it's going to have a signal wire. That signal coming out to the computer is a digital square wave. That could be a 5 volt, a 0 to 5 volt square wave. It could be a 0 to 10 volt square wave, a 0 to 8 volt square wave, a 0 to 12 volt square wave. That depends on the manufacturer. Again, you have the sensor itself, which, if you look, has a Hall effect device in it. It has a magnet, and it still has the metal reluctor, which is going to pass by the sensor. The difference is, instead of it just creating the analog voltage wave, the sensor is changing that analog to a digital signal and producing a digital square wave. So what we get here as this sensor is moving, we have a square wave. Now in this example, we have a 5-volt square wave. There is a 5-volt power supply. Okay, in the center wire, there is a ground, which is in this diagram called a low reference. And then we have a 5-volt on the signal wire, and that signal wire gets pulled to ground to create the signal. So we have a 0 to 5-volt square wave. Now, one of the big differences about this is when we go to open circuit or we unplug the connector, okay, you'll notice that ground is still ground, that's low reference, okay? But on the power supply, we should have a 5-volt power supply to power up the sensor, okay? And you can see here that we're at 5.01 volts on the center wire. And then we have the top wire, we have 5 volts also on that wire. That gets pulled to ground by the sensor as the reluctor is passing by. So that is what creates our 5-volt square wave. And this is an example of that. You can see here in the pattern that we're going from 0 to 5 volts. And you can notice that the square waves, while they are identical, they are offset from a little bit of each other, because one is on an exhaust cam and one is on an intake cam. So what we're going to do here now is we're going to discuss why those sensors are important. And why they are important is because the ignition timing and the fuel injection are controlled by the computer by the cam and crank sensors. And in order for the engine to get the proper performance, the cam and crank sensors let the computer know when to inject fuel, as well as when to fire the spark. And it is critical that the fuel is injected at the right time and that the spark is spark is fired at the correct time. So you can get maximum power and, of course, best emissions out of the system, as well, of course, good fuel economy, because the manufacturers want you to have everything. So the spark is absolutely controlled, and you can see in this that the computer is going to look at the cam and crank sensors to decide when is the best time to fire the coil. Okay, fuel should be in the cylinder already. It already fired the injector. And so when the spark is fired, it is normally somewhere in the 10 to 20 degrees before top dead center. That is because as that explosion happens, we're not going to get maximum pressure in the cylinder till you get a little bit past top dead center. So you have the spark actually fired before top dead center, but you get maximum pressure in the cylinder, and that's when you get the maximum push and the maximum power out. So we're going to switch over so you guys can see a live version of this in a minute. But I want to show you where we're going to make some connections on the vehicle. Okay. So what we have here, we have live in our bay a 2006 Ford Explorer with a 4-liter VIN-E engine. And we're going to connect a lab scope, a Pico lab scope, up to the crank sensor as well as the cam sensor. And we're going to show you what a live pattern looks like, and we're going to discuss that pattern in detail. So what we have first is our pins, and we can see here at the computer, we start at the top, we have pin 45, which is the cam sensor positive. That is where we're going to connect one of the leads of our scopes to. Okay, the pin 58 is our ground for the cam sensor. Okay, we are going to be grounded to negative battery, so we're not going to connect to that pin, but I wanted to show you that, again, that pin is going back to the computer. And then for the crank sensor, we are going to connect to both pins. We're going to connect to pin 46, which is the crank negative, as well as pin 47, which is the crank positive, because I want to show you something special about that crank sensor. Now, both of these are 2-wire sensors. They are both generating AC voltage. Okay, now some vehicles may have DC, may have Hall effect sensors, some may have AC, some may have a mix of both Hall effect and AC generating signals. It all depends on the manufacturer. This one has 2 AC generating signals. So we're going to go to the computer, we are going to connect to our 3 pins at the computer. Okay. So we're going to go to the computer and we're going to make our connection here at the computer. And you can see here that we have a blue lead, a green lead, and a red lead. The blue lead is on the crank positive, the green lead is on the crank negative, and the red lead is on our cam sensor. So we're going to show that on the lab scope here. First, we're going to do key on, engine off. And what I want to point out here is this is a live picoscope. Okay, I have a cursor here on the blue trace, and you can see here in the blue trace, we're about 1.6 volts, okay, on that blue trace. I could adjust that a tiny bit, okay, but we're about 1.6 volts. And on the green trace, we're again about 1.5. That is those DC bias voltage I was talking about, okay? That is on the wire as part of the DC. Now we're gonna create, notice that the cam has 0 volts on it, okay? So let me just straighten that a little bit better there, just to get a little closer to 0. That has 0 DC voltage. So only the crank has those DC voltage wires. As we start the vehicle up, what you're going to see here, and I'm going to freeze this pattern here in a second. We collected some. I'm going to freeze the pattern. And I'm going to shut it off so you guys can hear me better. What we have here is in the blue trace here, we have the crank sensor, okay? We have the green trace, which is the crank sensor. And in the red, we have the cam sensor. So first, I want to point out that this is this reluctor, this metal piece inside the vehicle, okay, on the crank, is a 36 teeth. There are 36 teeth in between the missing tooth. This is a 36 minus 1 reluctor. This is where the missing tooth is. It is a double wide. That's why it makes a little bit better definition here. Okay, so there are 36 individual pieces of metal on the reluctor. That means each one of these points is 10 degrees of crank movement. Okay, each one is 10 degrees. Notice how on the positive wire, the blue trace here, the voltage goes up. Now on the ground, you'll notice that the voltage goes down at this exact same point. They are mirror images of each other. The computer has to see the transition going positive in order for it to develop proper spark and fuel. And what I mean by that, if you made a mistake and you reversed the wires and you crisscrossed the 2 wires, the positive went to negative and the negative went to positive, you would get a pattern that looks like the bottom one on the positive signal. And the proper way would be on the negative signal. This vehicle would get no spark and no injector pulse because the computer has to see the transition going from positive on the positive wire when it's looking at that separation, that missing tooth. So it needs to see that. Now that missing tooth is different on different engines. Excuse me. On a 4-cylinder engine, that missing tooth happens at 90 degrees before top dead center. On a V6 engine, that missing tooth happens at 60 degrees before top dead center. On a V8 engine, that happens at 50 degrees before top dead center. So how does the computer count that? So if we were to actually look at this, okay, we have the missing tooth. Now I'm going to bring in a couple of cursors here. Okay, I'm going to put it right where it crosses the ground plane. Because that's, again, what the computer is looking for. So the computer is looking for that transition going positive, and that, this is a V6 engine, that is occurring at 60 degrees before top dead center. Okay, now, I'm going to bring in another cursor, And we're going to look at that same point where the cam sensor is crossing the 0 volts. Okay. Now, the computer is monitoring the cam as well as the crank. The crank is, of course, used for RPM. The cam helps to sequence the injectors in the right order, as well as firing the injectors at the correct time. So what we're looking at here is, if we were to count, remember, there are 36 teeth here. Each tooth is 10 degrees of movement. So I'm going to start with my mouse, okay? If we're at 0, or 60 degrees before, I should say right here. If we were to go over to this point, we're at 50 degrees before. Here's 40 degrees before, 30 degrees before, 20 degrees before, 10 degrees before, and then 0 degrees. That is 0. But if we notice, we got to keep going to where that cam positions. Now, for most Fords, okay, with these dual AC generating signals, that cam is going to cross ground at about 26 degrees after top dead center. So we were at 0. Here's a positive 10 degrees. Here's a positive 20 on this side. And if you were to add it over to that line, and my cursor is just going a little nuts here, let me get the mouse back. Where the line is approximately 26 degrees after top dead center, where the cam is crossing the 0 volt line. That is where it's supposed to be on this engine. So understand the computer is really good at counting, okay? And you can see here that it is looking, every movement of that reluctor is 10 degrees of movement. Okay, so the computer can determine every degree of movement. So we want to talk precision movement here. We are talking some precision measurement by the computer. The crank sensor has to be able to produce that in, and you can see here, the pattern is like almost perfect here on that crank sensor. Okay, and again, the negative side, the negative lead, which again is also raised about 1.5 volts here, is producing an exact mirror image of that signal. Okay, and just so you know, if you were to put your meter across the two, we would have a combination between the two signals, and that's what the computer is really doing here, is combining between the two signals. So the computer is using this to determine when to fire spark and when to fire the fuel injection. And this measurement is really important. Now, some different manufacturers, okay, are going to have different reluctors in their engine. Okay, they may or may not have a bias voltage. They may or may not have a 1 cam sensor. They may have 2 cam sensors. They may have 3 cam sensors. They may have 4 cam sensors. Okay, I have seen some with some engines with 2 crank sensors. I've seen some engines with 5 cam sensors. It all depends on the manufacturer. But the importance is they need to know exactly where the cams are and exactly where the crank is to make those comparisons. Now, when we're looking at this pattern again, and I'm going to start the vehicle back up. Again, to go live on the signal here. It is a Ford, and it did start on the first try there. Okay, and I'm going to go back to running. Okay, it is important to set up the scope here properly. So remember, the negative lead is on the negative battery. I got here the crank positive, we got the crank negative, and we got the cam. Notice that the trigger here is holding us steady. And I wanted to point that out because if we remove the trigger, we move where the pattern is drawn at. Okay, I can also, I'm going to try to steady that cam sensor by, I want to be. Just to steady that cam sensor here in the pattern here. And so I'm going to put it right about there. And just to steady that cam so it's not bouncing around as much. But I want to show, again, I want to show you the time here. This, and I'm going to freeze it again. And shut it off so I could talk so you guys can hear me. What we have is, again, we start at 60 degrees before, we end at 60 degrees before. That is one 360-degree rotation of the engine. Okay, we need a complete 720 to get a complete 4-stroke event. So I'm going to start it up again, and I'm going to put a little bit more pattern on. I'm going to change the time base up here. And now I'm going to freeze it again so we can see. You'll notice, again, here is my 60 degree before. So my 60 degree before, it's 360 degrees. Our 60 degree before. So now we have a full 720 degrees. That is a 1 4-stroke event. And notice we had one cam firing at 26 degrees after TDC, and they don't get another cam pulse until 26 degrees after 720 degrees later. So we went through all 4 strokes here, and we came around one complete 4-stroke event before, again, that cam fires, that cam sensor crosses again. There's a relationship between, again, 2 revolutions of the crank to 1 revolution of the camshaft in any 4-stroke engine for the most part. Okay, there's always an exception out there, but for the most part. So this is the precision measurement that the computer is doing to make sure that ignition and fuel delivery are proper, as well as, ignition timing, the shifting of transmission points. The RPM signal is an important signal. Cam and crank are important to everything that the vehicle needs to run properly. And of course, that precision measurement what helps us make that. All right. I just want to say, I want to thank everyone for coming out tonight. Now, I also want to say thank you for coming to my lunch. Remember that the sensor design is extremely important, okay? And you got to have that precision sensor to make those precision measurements that the computer design depends on. I want to open it up to any questions. Anybody have any questions at all about anything we talked about today?
It looks like the only question we have coming in now is obviously you're using a picoscope for the data that you pulled up. Are there any other recommendations for other lab scope equipment that would give you as good of a good data pull down like that you've used in the past?
Well, so a picoscope is a very good automotive scope, but there are many other automotive scopes out there that can do a similar job. Autel has them, Snap-on has them. Okay, there are many available for even 1-channel lab scopes can help you get a pattern online. So there are many different options out there. Now, I prefer the Pico, but I'm also pretty, I like Snap-on as well. It's the ease of Snap-on. The setup of a Snap-on tends to be a little easier than a Pico because there's, it's designed differently. Okay, but the Pico gives us the most powerful punch that's to look at. In my opinion. I want to thank everyone for coming out. And if you have any questions, please let us know. See us on the next Power Hour. Look forward to the next Power Hour where we will bring it to you from Standard Motor Products. Thank you so much. Have a great afternoon.